Good morning, everyone. As we get started on this term, I thought it would be useful to look at what physics is supposed to be about. For some of you, if not most of you, this is the first physics class that you've ever taken. So what's physics about? I mean, people have talked about this with me in the past, uncles, aunts, moms, dads, brothers, sisters, perhaps, and oftentimes people are scared about it. But really what physics is all about is how putting together a model of how we look at the world. We say that physics is a foundational science because it underpins a lot of the things that we see in other sciences. So as we get started here in this particular discussion, I'd like to kind of lay out what we plan to talk about here. And the first thing that I would like to discuss is really the what of physics. What is it? What are the structures of it? What's the whole point? And that leads us to the why of physics. Why do we do this? If I'm a bio major, or I'm a chem major, a math major, an engineer, why are they making me take this physics course as a requirement for my degree? And finally, I wanted to talk a bit about the how of physics. And the combination of answers to these three questions lay out what's not only specific about physics, but how physics relates to your particular field. Now, that's what we'll spend a little bit of the beginning of this talk about. But eventually, as we answer these questions, we're going to find out that there are a couple of important things to keep in mind as we're doing physics through the whole term. One of the things that we're going to find is that we have to keep track of things called measurements. Measurements have different parts and things associated with them. And part of this discussion is going to be learning about the System International system of units. This is not all of what we use here in the States. We often use an English set of units, and so there may be some conversion factors and the like. There are some convenient things to keep in mind. Multipliers that give us easy ways of thinking about SI units and the advantage of using SI units as opposed to other systems of units. We're going to learn a little bit about something called sig figs, significant figures, which tells us how good our measurements are. And this set of how good our measurement is coded into SI units. It's coded into how we want to take measurements. And so it's really convenient to keep track of in our minds. Now, the whole point is, sure, measurements are going to be important, and that's not a huge surprise, but it's also useful to keep in mind what we're trying to measure. And from that comes something called dimensionality, or dimensions. So what are dimensions? It's the kind of things that can be measured, and this could be something as simple as length, it could be something as simple as time, but it could be something more complicated, such as, what is the area or the volume of some object? How fast is the object moving? How is the speed of some object changing as a function of time? And all of these things have different kinds of units. Some of these units are pure and built into SI, and other units are something that are called derived units. And once we know something about units, whether they are pure or whether they are derived, we can start to do something called dimensional analysis. That tells us whether the things that we're trying to measure, the math that we're trying to do, the expressions that we're trying to build actually even make physical sense. And finally, part of the dimensional analysis is something called unit conversions. And while it seems pretty straightforward, it turns out that certainly here in the States, we have to pay more attention to things like unit conversions, because we often have to convert things like, a mass in slugs to a mass in kilograms, or we have to convert a length in miles to a length in kilometers. And so knowing how to do unit conversions is something that's pretty important. Now, after we've done that, there's going to be some examples and whatnot. But a final thing that's going to be very useful as a tool that we use throughout the term is something that's called estimation. We're going to have to be able to make estimates of whether things that we are measuring make any sense. So very often, as we've been trained, we go through our training and we might be given some math problem, might be given some science problem, but we're not necessarily given context to these problems. We have to figure out the context for ourselves. And so as we get older and get a little bit more sophisticated, that becomes something called word problems. And so this information gets given to us in a sometimes complicated way, and we have to sift through what is given to us to sort out what makes sense, what doesn't make sense, what's necessary and needed, what's not necessary and needed. And finally, at the end of the day, after doing our analysis, we also have to assess whether what we have makes sense. If we were asked to find the area of a typical desk, and we find something in units of kilometers squared, we clearly did something wrong, because I've never seen a desk that big before. In fact, a desk of that size is going to be roughly the size of a football field. Actually, it's going to be a pretty fair fraction of a town. So obviously something went wrong, and we need to assess and figure out whether the answers that we're calculating make sense or whether they don't make sense. And through the whole process of going through this, there are going to be some examples that we do as well. If you're going through the course shell on Canvas, you're probably going to see more examples than you're going to see in a video like this. This is intended to give some flavor if you like the more traditional lecture format. But really, you can get all of the stuff that's going on here if you can do a little bit of reading and you can go through the examples that are worked out. This is just a different format of the same thing. So this is going to be a rough overview of what we are doing today. Okay, so let's get started. First of all, we want to answer, what is physics? Well, typically, if you're just stepping into a scientific background and a degree program, you just know you have to take Physics 1 and you have to take Physics 2. Okay, wonderful. Well, what is in those physics courses? Well, typically in a Physics 1 course, you're going to be looking at something called mechanics, and often at the end of the term, you'll look at something called thermodynamics. What is mechanics? Mechanics is looking at essentially the motion of particles. There's three different ways that particles can move. They can move translationally in a straight line. They can move rotationally around some pivot point, and they can have repetitive or oscillatory motion, where things go back and forth. And in the process of looking at how this object moves, we look at things called velocity, position, acceleration, and how those change as a function of time. We find out how acceleration comes about through forces. Okay, wonderful. Are there other ways to do problems? We find out about energy and momentum, and how energy and momentum are coded into this particle as well, through its process of moving, through its process of accelerating. Okay, how do we apply all of these principles of position, velocity, acceleration, time, force, energy, momentum? How do we apply that to different actual applied problems? How do we make fluids flow, for example? How do we look at planetary motion, the motion of planets around a sun, or moons around a planet, satellites around a planet, those types of things? How do all of those rules and laws apply? And that's really what mechanics is all about. Whether we're looking at translation, whether we're looking at rotation, or whether we're looking at oscillation. Typically at the end of a Physics 1 term, you get into something called thermodynamics. And for those of you that are in chemistry and biology, this is a little bit more near and dear to your heart, because here's where we're talking about heat and the equivalence of heat to energy. So you could be looking at how energy being delivered to some problem can take various sorts of forms. And in your bio class, this might turn into a way for a cell to immobilize. In a chemistry course, this might lead to a reaction going forth or not going forth. But in a physics course, energy takes different forms as well. Now, once you're through physics 1, you go into physics 2. And physics 2 is often looking at electromagnetism and optics. So we learn a lot of terminology for how different objects can interact in physics 1. But in physics 2, we apply that interaction to charged particles. So it turns out that charged particles with plus or minus charge interact with each other. They can put forces on each other. There's energy that can be stored in these systems. Okay, that's good. Not only that, currents or moving charges can interact with other currents. So there's forces there. There's energy that's stored in that kind of system as well. Part of electromagnetism is learning about circuits. Resistors, capacitors, inductors, batteries, how they are arrayed in certain manners to make detectors and sensors of various kinds. So this is really what electromagnetism is about, and that culminates in something called optics. Inside of the creation of light and radio waves and microwaves and ultraviolet and infrared, is really a culmination of electromagnetism and the rules that we learn in electromagnetism. So optics is sort of that on steroids, but we learn how glasses work and we learn how mirrors work and the like, as well as how light is reflected and refracted going through different kinds of materials. That's how your eyeglasses work. So that's the physics 1 and physics 2, and it's the kind of physics that 75% of you are going to be needed to do your science degree. If you continue on, you get into the more interesting things that play around with your mind and imagination a bit by learning about relativity and quantum mechanics. These are often, in some schools, this might be called physics 3. Here at FAU, this is called Survey of Modern Physics, because these two topics came about 100 years ago. And in comparison to the many other kinds of physics that we are learning that are many hundreds of years old, it is a relatively modern phenomena. And we're still learning the details and intricacies of general relativity in particular, quantum mechanics, and how it applies to actual physical systems. So that's really, what is physics? But another question is, why do we do physics? As I said, many of you are sitting here in your maybe a chemistry major, or you're a biology major, and they're forcing you to take these physics courses. And I really don't want to. I don't see the real application. And it turns out that physics is called a fundamental science, not because it's more important than biology, not because it's more important than chemistry. It's because the rules that we learn here give the rules for how things are going to work in other courses. The topic of energy in a chemistry course, you might say what energy does. In a biology course, you might see what energy does. In a physics course, we try to figure out, okay, what is energy? In a biology course, maybe you're a physical therapy major or something like that, and you need to learn about applications of forces or applications of stress. But in a course like this, we learn, what is stress and what is force, and how does our perception and thought about what a force is, how does that compare with what really a force is all about? So there's a bit more philosophy associated with a course like this. But we also try to come up with a toolkit for coding these observations, these measurements, these things that we want to discuss, code these things into math. And often then it prizes simplicity. How do we figure out which of the parameters that we know are important, which of the parameters that we know aren't important, and put all of those things together? And that's really why you are in here, to learn physics, is to learn that kind of tool. But a final thing that we want to keep in mind is, how do we do physics? And that's really maybe laid out in this page that's in your notes as well. The whole point of physics is really to come up with laws and theories. And it's a common misperception to say that a theory can grow up and become a law. That's really not how it works. It turns out much more accurately what goes on is we can take a whole bunch of measurements, see a whole bunch of observations, and we start to recognize that there are patterns. And some of the analysis of these patterns, in order to have predictive value in the future, we need to see what we think about these patterns, see what we think about this data, what's recognizable and not recognizable, what things led to different sorts of behavior. A windy day, certain thing happened, and when it wasn't a windy day, something else happened. If I turn this particular knob, something changes, and if I turn this other particular knob, nothing changes. These sets of observations and measurements allow us to see the world and make predictions. And one of these things that we can do through this process of looking at the measurements and stuff is the measurements and the data and the observations is to come up with a hypothesis. What do we think is happening? And what do we think is important? Then we go about testing this hypothesis. And part of that testing of the hypothesis is, can I come up with a mathematical expression that says what's going on? So this knob gets turned in a particular way and something happens. Something seems to be going on in a particular region of space, and it doesn't happen in that exact same way in another region of space. What's different between those two regions of space? We want to code those differences into some mathematical expression. That's what we're doing when we create a law. We are basically telling a what is going on. We don't say why it's going on, and it takes a lot of observations. It takes a lot of measurements. It takes even a fair amount of understanding and testing of our hypothesis to come up with such a mathematical expression. But the law is saying the what. And as we go through the term, there's lots of laws that we're going to look at. There's Newton's laws of motion. They're coded into a mathematical expression that says what happens if you set something up. Or Newton's universal law of gravitation. What happens if you have two masses that are in the vicinity of each other? We have Bernoulli's law. What does Bernoulli's law say? It's a mathematical expression of a setup of certain values and parameters. Okay, wonderful. So that's what a law is. So what's a theory then? It is our estimation of why something is going on. And we don't really know why something is going on. Oftentimes, as more data comes in, our explanation for why something might be happening changes. Our hypothesis changes. Why we would want to do some testing to test our hypothesis changes. Our expression of the law might change with more data and more experimentation and more observation. But the theory is some sort of model as to why something is happening. The theory of gravity is, this particular thing is coming about because of some particular thing that's going on. Something is happening in the universe in some particular way, and this is our best understanding of what's going on. That's why there is a theory of gravity, but there's also a law, Newton's universal law of gravitation. They're looking at different aspects of the same problem. One is looking at what, one is looking at why. Okay, so one thing to keep in mind as we continue on with this discussion of, what is physics, why is physics, and how is physics, what physics is really all about is not a discussion of truth. Physics is about a search for the truth. That's what we're trying to do here. And as we get more data, we are able to change our hypotheses. We are able to change our laws. We are able to change our theories to get a better understanding and a better application of our understanding to the physical world. It's not about truth. It's about the search for truth. It's about the search for truth. And that's why, you know, here in a course like this, we're going to learn about Newton's laws of motion. And if you were to continue on to a modern physics course, we learn about Einsteinian relativity. Well, does that mean that Newton was wrong? No, it doesn't mean that he was wrong. It means that maybe as we probe and push things in different ways, there's a greater richness of complexity that comes out that Newton wasn't able to probe with his initial understanding. It doesn't say he's wrong, but it means that the search for truth can alter the way that we perceive things. And so we still talk about Newton and his laws of motion today, and the fact that Newton was a genius, even though if we were to push his problems a little bit harder, things actually go in a different way. So as we keep going here, I'm going to look a little bit at measurement. So we have the what and the why and the how of physics. Now we need to actually apply, do some stuff with it. And the first thing that we really need to do is to take measurements. This is what the science is all about, and it's true whether you're a chemistry major, it's true if you're a biology major, if you're an engineer, you need to be able to take measurements. And measurements are comprised of at least two things. You need to have a number of something, and you need to say what something's that number is. So what I say that is here is you have to have a size of something, and you have to have some unit standard. And here, what you see on your screen is a couple of good examples. Maybe I have two measurements. One of them is 3 miles. Another one is 0.5 kilograms. So in this expression, I have two parts. In the first one, I've got miles. It has a particular unit. What do I have 3 of? What do I have 5 of? What do I have 10 of? It is this thing called miles. Could it just as easily have been feet? Could it just as easily have been meters? Could it just as easily have been seconds? Sure, it could have been any of those things, but I have a certain number of a certain thing. I have a certain number of a certain thing. And this is what a measurement needs at least. Actually, a little bit later in today's lecture, when we learn about vectors, we find out that certain measurements not only have a size, but they have a unit standard and they have a direction that we might have to keep track of. So, but at its simplest sense, we have to be looking at a certain number of a certain thing, and that's what a measurement is. Now, that being said, you know, what if we were to relate this to miles to kilometers? Well, what's a kilometer? It's actually a multiple of a meter. It turns out a kilometer is actually 1,000 meters. So sometimes through this, here, we can take a look at this first. Let's look at SI. This gives us a sense of what are the kinds of things that we can measure. What are the least number of dimensions of things to really get measurements of things? And this is what SI is really all about. It is boiling down to the simplest possible parameters what are important dimensions and dimensionalities. And the ones that are listed here that are highlighted, length, mass, time, these are the ones that we really deal with in this particular class. We need to know that a meter is a particular length. We need to know that a mass is a certain amount of material, so to speak, calculated in a slightly different way than the mole that's shown a little bit later. A time is the passage of time. And some of these things are already built into our heads. It's kind of weird when you see it written down, and it's kind of weird when we have to figure out some definition for what's going on. This is really odd. Now, that being said, all of these different dimensions are going to be used through the course of a physics term, Physics 1 and Physics 2 together. So just because I don't have temperature highlighted doesn't mean that we're not dealing with it this term. That's what thermodynamics is at the end of the semester. Electric current. Just because electric current is not highlighted here, you'll see that in Physics 2. That's going to be important. Luminous intensity, the candela. We don't see that in Physics 1, but you could see that dealing with optics in Physics 2. It's going to be somewhat important. And actually through the thermodynamics at the end of this term, and if you were to continue on into quantum mechanics and its application to chemistry, the mole at the bottom is going to be important as well. Now that said, these are the basics. This is the bare minimum of things that you really need to know to figure out what's going on. And sometimes for the kinds of things that we want to measure, man, it would be really nice if we could keep track of them in a slightly different way. So let's say, for example, we had a measurement of 3,000 meters. And having to keep track of all of these zeros is kind of a hassle. Is there an easier way to write this? And because of the way that SI works, we come up with this thing called multipliers that say, you know what, you can keep track of a certain number of zeros in your problem, certain multiples of 10 in your problem, with certain prefixes to the unit. So here we've got 3,000 meters. There is a special multiplier called the kilo, which means 1,000. So if you have 3,000 meters, why don't you just write that as 3,000 meters? And that's what that K is all about. Kilo means 1,000. So this is a compact way of writing 3,000 meters. And maybe when it comes to 1,000, it's not really such a big deal, right? But what if it was 6 zeros? What if it was 9 zeros, or 10 zeros, or 12 zeros, or 15 zeros, or 20 zeros? Oh, wow. This could really get out of control, and I'd have to really pay very close attention to what I'm doing in terms of my measurement if I had to keep track of all of those zeros. Not only writing them down, but reading them off later. So these prefixes can actually be very important. And you'll see here from this table from the book that we have prefixes that not only describe multiples of 10 in a bigger sense. So here's 1,000, here's 1,000,000, here's 1,000,000,000, here's 1,000,000,000,000, here's quadrillion as you continue on. We can keep track of all of those zeros with different prefixes like kilo, mega, giga, tera. And some of these are probably familiar to us through computers, where we can have bytes and kilobytes and megabytes and gigabytes and terabytes. That's how we can use those, through certain multiples of 10. And in these cases, for these prefixed values, it's multiples of 1,000. But we can also go the other way for things that are very, very small. 0.1, 0.01, 0.001, 0.000001. You can see, wow, that's even more confusing. So once again, we can keep track of how many zeros we have in our problem by using prefixes. And something like 0.1 is actually 1 deci, or 0.01 is 1 centi, 0.001 is 1 milli. So we can use other sorts of prefixes to keep track of zeros on the other side, between some decimal point and some measurement. And it could mean millimeters. That seems pretty reasonable in our head for what a millimeter might be from a ruler. Micrometer, maybe not as good of an understanding. Nanometer, even less so of a good understanding. But it turns out that whether we have a lot of zeros after a number to make a big number, a lot of zeros before a number to make a very, very small number, prefixes can be very important. But even with these prefixes, it's not everything that we want to know. We also want to know something about the precision or significance of our measurements. And so I want to talk a little bit about significant figures, or sig figs, before we continue much further. So let's say I was to take some measurement, and I said that, I wanted to measure maybe the height of my room that I'm sitting in here. Okay, well, it's roughly 2 meters. So I could say it's 2 meters. Okay, but is it really 2 meters? I mean, you said it's 2 meters, but is it really 2 meters? Well, given the precision that I have with my eye, yeah, it's 2 meters. But if I got out a meter stick, I might find out that it's 2.3 meters. So that extra digit gives an implication that I know the height of my ceiling a little bit better than my initial measurement of 2 meters. 2.3 seems to have more precision. And that 3 being there says that your measurement of 2.3 as opposed to 2.4 as opposed to 2.2 is a better measurement than 2. I've got a whole other decimal place of precision. So that last decimal place seems to be important. And if I was to say that the height of my ceiling is 2.34 meters, that is giving an implication that I know even better what the height of my ceiling is. The measurement that I've made has more significance to it because it's a better measurement. The more numbers that we add on to the end, the more significant our figures. And when we're adding numbers like 2 or 3 or 7 or 8 or something like that, it has an implication immediately of significance. But if we're adding a 0, the 0 might have actually been something that we measured. That thing that I said where the height of my ceiling was 2 meters, it could have been 2.00 meters. That's 2 meters, but it turns out that that says that I know the height of my ceiling to more significance. That 2.0 says that, it's not 2.1 and it's not 1.9. It's actually 2.0. And 2.00 says that it's not 2.01 and it's not 2.19 or 1.99. It's 2.00. Zeros can also have some significance. So how do we figure out how good a measurement is, and how do we tell other people how good our measurement is? That's really what significant figures are all about. And so what I have here on the screen is a measurement of 18.23 somethings. I don't know, buckets, meters, seconds, I don't know. But it turns out here this last digit is something that tells the significance of our measurement. It says how good it is. We know this particular number to 1 part in 100, to within 1% is what the implication of this thing is. Similarly, over here, we can also write our units in something called scientific notation. And in scientific notation, there's this first numerical part, and then there's a times 10 to some other numerical part. This first part in scientific notation is actually called the significand because it tells you the significance of your measurement. 1 times 10 to the 3, 1.3 times 10 to the 3, 1.30 times 10 to the 3, all kind of look like around 1 times 10 to the 3, but they're different values of significance. How good we know that measurement. And significance is really coded into scientific notation, one of the reasons that we use it. And when we're not using scientific notation, there really can be ambiguity. Here is another measurement that I have here. I don't know if it's buckets or seconds or meters, but the numerical part of it is 1300. And so now I look at a number like this. Is that 0 a placeholder? Or does that 0 have significance? Is it 13.00 and not 13.01? Or is it 13.00 and not 1310, 1310? Or is this just distinguishing between 1300 and 1400 and 1200? The way it is written, it's not exactly clear. So oftentimes what you would want to do is use a combination of multipliers or scientific notation to relieve that ambiguity. So say this 1300 was 1300 meters. If I was to write it in kilometers, then all of a sudden I can see, it was this 0 that was significant. The green one is the one that I was keeping the significance on. I don't know anything about what's going on with red. The red one was just a placeholder because of the way that I wrote it down. It works the same way as it did in scientific notation, which is kind of nice. Now, we're eventually going to be taking these measurements with varying degrees of significance and putting them together. And maybe I'll be adding 2 lengths together to get another greater length. That's fine. Maybe I'll be taking 2 lengths and multiplying them together to get an area. Or 3 lengths and multiplying them together to get a volume. Or a length and a time and putting them together in some way as to create a speed or a velocity. So if we are adding things together in terms of scientific, the precision and significant figures of an operation, when we are adding, the least precise place is preserved. So if we've got decimal places here, here I've got something with 2 decimal places, here I've got something with 1 decimal place. 1 decimal place is less precise, so that is the place that is preserved upon addition. So I might have put it into my calculator and got 15.34 when I added those 2 numbers. But because I was adding, I can only keep the least precise place. That means 15.3. It doesn't mean 15.34 because it's not that precise. One of our measurements wasn't good enough to warrant that significance. If we're multiplying things together, the least number of significant digits is preserved. So here I'm multiplying something with 3 significant digits times something with 1 significant digit, which means if I put it into my calculator, I would get 4.05, it comes out. But I don't know my answer to 3 significant digits. One of my measurements wasn't good enough for that. And because one of my measurements is poor, I can only say that my answer is 4. I can't say it's anything more or less than that. And that's how significant figures work together. Okay, now this gives us some sense of working with the numbers. That's what multipliers and significant figures are really all about. But I want to talk a little bit about dimensions as well. And if you're curious, if you wanted to figure out what different lengths and times and masses were all about, you can look at that here. But I want to talk a little bit about dimensionality as well. And in SI is coded the base fundamental dimensions of things like length and time and mass. But a lot of things that we want to measure and a lot of things that we want to discuss are combinations of these fundamental base dimensions. For example, if I wanted to measure an area, I have to take a base times a height. And the base is measured in meters and the height is measured in meters, which means an area is a meter squared. So I create something called derived units by putting combinations of fundamental units together. In this case, area is a derived unit of meters squared based upon the fundamental units of length and length. But there's other examples that we're going to see through the term. We could have speed as a meter per second, acceleration as a meter per second squared, density is a kilogram per meter cubed, volume is meters cubed, a force is kilogram meter per second squared, and sometimes these things get special other names. We group all of these things together to make something else. In the case of force, a kilogram times a meter divided by a second squared is something that's called a newton. So if you ever see newton, it's not a fundamental unit. It is an SI unit, but it's an SI derived unit. It's built upon other things, in this case, the kilogram, the meter, and the second, put together in some special way. And if we're going through other sorts of topics, there's going to be a special derived unit for energy, and there's a derived unit for momentum, and there's a derived unit for all kinds of other things that we're going to see. So this just kind of keeps in mind what this dimensionality is. And why is it important? Because it turns out that as we're putting things together to come up with some final expression, say we were taking 2 lengths and multiplying them together to get some area of something, we know that as we're putting these things together, I know what the units of area are. And so as I do the mathematical manipulation, I have to get that coming out as a result. And the way it works is through something called dimensional analysis. These units that we're talking about, whether they are fundamental or derived, are algebraic. What does algebraic mean? That algebraic means that they work like units in algebra. So I can only add like things together. I can only multiply things in certain ways. And when I multiply things in certain ways, the combination of those things is still there, grouped in the way that they were grouped in the mathematical application. So one example of that is here, something that we're going to see in Unit 3 on force coming up later. I know that force is a mass times a length divided by a time squared. So in my expression for force being equal to mass times acceleration, this is going to be something that we call Newton's second law. This is a simplified form. This isn't really Newton's second law, but we'll get to that when we get there. If I was to take a mass and multiply a length per time squared, then mass times length per time squared has all of those units and dimensions working the way that they're supposed to give me a mass times length divided by time squared, and this being something like a Newton. So I can take a mass times a length per time squared, which is an acceleration, and get a Newton as a result. That's why force equals mass times acceleration gives an expression that algebraically makes sense. And in a more basic fundamental way, when we learned algebra, I knew that if I had something like 3a plus 4b, I can't really simplify that anymore unless I know how b relates to a. And in a lot of problems, b doesn't relate to a. What if a is meters and b is seconds? I don't know what it means to add those together. That doesn't even really make sense. We're not adding the same kinds of things. So that's really kind of weird. So I can add two lengths together and make a different length. I can add two times together to make some different time. But I don't know how to add a time and a length. That doesn't even really make sense. But that's because of our understanding of algebra. So what if a and b were really just different expressions of the same dimension? Maybe there's some conversion factor for, okay, well, a is meters, but b is kilometers. They're not exactly the same thing, but they're measuring the same dimension. They're both measuring a length. And there is a way that we can relate kilometers to meters. A kilometer is just 1,000 meters. So, yeah, I can add 1,000 meters to a meter. That's the kind of thing that could be done. So sometimes through algebra, there is a conversion factor that allows us to put all of these units together into something that is agreeable. That would be like having a 3a plus 4a. And I can certainly add 3a plus 4a, or 3 kilometers plus 2 miles. Those are both lengths. I could add those two together as long as I agree on what the unit is going to be. Are we giving our answer in miles, or are we giving our answer in meters or kilometers? That's just something that we have to understand. And algebraically, 3a plus 4a equals 7a makes a lot of sense because we're just adding together different a's. Now, we don't have to be so specialized when we have multiplication. Just like above, I could take an acceleration times a mass and get a force. That's totally fine. I didn't have to do a whole lot of conversion for that. And so doing things like 3a times 4b means that what we're doing is creating a new unit, an a times b unit. And up here, that would have been a mass times a length divided by a time squared, or kilogram meter per second squared in SI units. But dimensions tell us about these algebraic quantities. If you have different units on one side of your equation than the other side of your equation, then you have done something wrong and you need to fix it. Okay. Now to do that, the last thing we want to look at is a conversion of units. So sometimes we need to turn something into something else. And the way that we do that is to keep track of the algebraic nature of the units, but we want to multiply times different forms of 1. Because I can take any number, multiply by 1 without changing it. So when we're converting units, what we're doing is taking advantage of that fact. In this example that you see here, I want to convert 80 miles per hour into the same speed, only expressed in meters per second. Miles per hour might be what I know from my car. Meters per second is something that's going to be useful in this class. So the way that I can do this is to recognize that 1 mile is the exact same thing as 1,609 meters. Those are exactly the same thing. So if I was to take 1 mile and divide by 1,609 meters, that's 1. If I was to take 1,609 meters and divide by 1 mile, that's 1. because they're the same thing. I take A divided by A, that's 1. If I take 27 divided by 27, that's 1. So I can multiply 1 times whatever I want. And the same thing is true here. 1 hour is 3,600 seconds. So 3,600 seconds divided by 1 hour, that's 1. 1 hour divided by 3,600 seconds, that's 1. So what I'm doing here is taking one unit, some measurement that I happen to know, 80 miles per hour, and I multiply by 1. And I multiply by 1. That means it's the same thing as 80 miles per hour. But what I can do algebraically is recognize that hour is on top and hour is on the bottom. Those cancel out algebraically. Mile is on top. Mile is on bottom. They cancel out algebraically. It leaves behind meters on top, seconds on the bottom. And here, so what I'm doing is taking 80, multiplying by 1609, dividing by 3600, having units of meters per second. It turns out that 35.8 meters per second is the same thing as 80 miles per hour. They don't have the same units. They don't have the same number. But they are the same thing. Because all I did was take something, multiply by 1, which means it doesn't change, multiply by 1 again, which means it doesn't change. Pretty cool. So using this, I can convert all kinds of different things. And in fact, this particular example is useful because it tells us that 35 is about the same thing as 40. So 80 miles per hour is about the same thing as 40 meters per second. Or 2 miles per hour is about the same thing as 1 meter per second. So now through the process of this course, when we see some speed in meters per second, we can multiply by 2. That tells us how many miles per hour, roughly, we're at. And this roughly qualification is what leads us to our last topic on estimation. So before I was talking about how high is the ceiling in my room. 2 meters? 2.3 meters? How good do you need to know? How long did something take? An hour? 1.5 hours? 1 hour and 15 minutes? How good do you need to know that time? And maybe you don't even really have a good way to get specifics, but you want to get in the right order of magnitude of what's going on. Maybe you need something that's able to be calculated quickly. And you don't want to wait for the actual results. You want to get something that's close and quickly. And so shown here is basically an example from the days of the Manhattan Project, trying to come up with the atomic bomb, and you're in a race with the Nazis to get there first. And so, one of the giants of physics, Enrico Fermi, he was seeing one of the test detonations of the first atomic bomb in New Mexico. And he didn't want to wait for the final measurements of what the yield of the bomb was and the blast radius of the bomb was and all these sorts of things. He said, with a couple of quick measurements, I can, at inspection, figure out the right order of magnitude of what's going on. I don't have to wait 2 days for the actual measurements. I can start doing things with information immediately, minute 1, by just knowing how to make some quick, simple, rough measurements of how things are. And sometimes that's really all you need. So let's say we were to look at an example of using estimation and orders of magnitude. Maybe we want to look at a problem like this. How many times does a human heart beat during a lifetime? How many gallons of blood does a heart pump? And you think to yourself, I don't have enough information for this. I don't know. How long does a person live? Is every heart exactly the same? Does everybody's heart rate stay the same throughout their lifetime? Absolutely not. But we have some sense of what the pace of a heartbeat is. We have some sense of how long a typical person is going to live. So we could start to make some estimations of what are the answers for something like this. They're not going to be exact, but maybe they're good enough. So let's say we were wanting to do this kind of an estimation. Do we have a guess at how fast a person's heart beats. And I might think to myself, I don't know, dum-dum, dum-dum, dum-dum. That's like a heartbeat. Is it once per second? Maybe a little bit more than once per second? Maybe a little bit less than once per second? Yeah, I might think to myself that there are 60 beats per minute for a heart. Okay, well, that's a good place to start. But you're not asking for, beats per minute. I want to know some certain total of beats in a lifetime. So I might have to do some conversion. I know that there are 60 minutes in an hour. So now I can get beats per hour. I know that there's 24 hours per day. So now I can get beats per day. There are 365 days per year. This gives me beats per year. A typical person, 75 maybe years is a lifetime. And these are just guesses. I don't know if these are true or not. But these are reasonable estimations. I'm certainly knowing that I'm converting minutes to hours to days to years correctly. Does a person live 75 years? A lot of people don't. Some people live more. But this is a fair number. Is the heart rate 60 beats a minute? Is it 70 beats a minute? Is it 70? Sorry, I don't know who's calling me. Sorry, I apologize for that. So maybe this isn't a great number, but it's a fair number. And that's the whole point. And that once we know these kinds of numbers, I could come up with a ballpark guess of what we have going on. So let's pull out our calculator here. And here we've got 60 times 60 times 24 times 365 times 75. Okay, so using scientific notation can be a little bit easier. What we see here is that the number of beats per lifetime is about 2.3652 times 10 to the 9 beats per lifetime. Now, how good are our measurements? I was putting 60 beats in here. I didn't put 65. I didn't put 55. I put 60. So I would say that I only have one significant digit here. Now this is a real conversion. It really was 2 significant digits. It actually is as much significant digits as we want. And 24 hours in a day. That's as many significant digits as you care to have. 365 is good to at least a day. Okay. 75 years, I don't know. That's 2 significant digits. But as I'm looking at all these things multiplying together, this was probably my poorest guess. 60 beats a minute. It's only good to 1 significant digit, which says that what we know is that roughly we have 2 times 10 to the 9 beats per lifetime. This is an estimate that's maybe a little bit better than 3, a little bit better than 1, but it's representative of what we can expect. Now, knowing this kind of data, we know how many beats in a lifetime or whatnot. We're also asked to find out how many gallons of blood get pumped in this same lifetime. So I might see that every pump gets 50 cubic centimeters of blood per pump. So I've got maybe this many beats per lifetime, and I'll just keep that number in my calculator. So I know beats per lifetime And this is that number that's already in my calculator. But now I need to do some conversions because I don't want beats per lifetime. I want some sort of a volume per lifetime. So maybe I see that with each beat, I've got 50 cubic centimeters of blood per beat. So now I've got, using a different kind of calculation, because the beats are going to cancel out, now I'm starting to look at something like volume per life. It's not in the right units. I need to do some conversion of units. So a cubic centimeter, there are 1,000 cubic centimeters in 1 liter. So now, centimeters cubed, I've got liters per lifetime. Okay. And maybe I know that there's 3.8 or so liters per gallon. Now, I've got gallons per lifetime. And going back to our calculator, I can multiply this by 50, divide this by 1,000, and divide by 3.8 to find out that we have 3.11 times 10 to the 7. But again, our best estimate here was one significant digit. So this is 3 times 10 to the 7 gallons per lifetime. That's what we actually measure for a problem like this. Okay. Now, how good is this? It's good to within 10 million gallons. This is good to within 1 billion beats. So it's not a terribly great number, but it's a fair number, and it gives us a way of estimating whether the things that we're trying to do make any sense. Now, before I end this part of the lecture, I wanted to look at one more thing. Because through your training in science, you might have been trained to, if you're given some number, to use that number right away. And that's actually not a good strategy in a course like this. In a course like this, you want to do your analysis in a different way. So say we're looking at a problem like this. In this problem, those same Manhattan Project scientists were at Los Alamos, and they found that if you have a certain volume, a certain mass of neptunium that's bigger than 60 kilograms, it will start to fission, and it will become a bomb, or it will become a nuclear reactor or something like that. And this neptunium has a certain density, so we know a mass and we know a density. We would like to figure out how big of a sphere of neptunium we need to have this critical mass. And normally we think to ourselves, oh, well, this problem is relating to neptunium. This problem is relating to the density of neptunium. This problem is related to a certain particular mass of neptunium. But that's really not what's going on. So in this problem, sure, we were told what the mass is. And if I wanted to, why couldn't I just algebraically say that the mass is m? And maybe I'm told what the density is. And why couldn't I just talk about that density algebraically in terms of some variable? Greek letter rho is typically what's used. Now, eventually, we're going to be working with some sphere. And spheres have a couple of important parameters. Maybe there is a radius, r. Maybe there is a volume of the sphere we could call v. And for a sphere, the volume of a sphere is 4/3 pi r cubed. Now, this doesn't have anything to do with our particular problem. Every sphere has a volume 4/3 pi r cubed. Every sphere has a radius. Every material that we could want to work with, every sphere is going to have some particular mass. And because it has mass and volume, it's going to have some particular density. So this isn't so specific. This just tells us how the radius, volume, mass, and density of some object relate to one another. So in this particular problem, maybe we're wanting to solve this, and I say that, you know what? In this problem, if I wanted to calculate a density, I know from when I was a kid, density is mass per volume. Or I could say that density is the same thing as mass per volume, like so. Okay. And I've already said that the volume of some sphere is 4/3 pi r cubed. This volume and this volume are the same thing. So why don't I just write this algebraically as the same thing as mass per density? Algebraically, density being mass per volume is the same thing as volume being mass per density. Okay, this volume are the same. So what we are saying is that 4/3 pi r cubed is the same thing as mass per density, algebraically. This is true for any sphere. This is true for any mass. This is true for mass formed into a sphere. This is true for any material, neptunium, carbon, iron, whatever you want. And so now, from this relationship, if I want to find radius, I just have to solve this algebraically. So if I multiply both sides by 3 and divide both sides by 4 pi, I see that r cubed is equal to 3m over 4 pi times the density. And if I want to find the radius, it is 3m divided by 4 pi times the density to the cube root. Now let's say I'm actually looking at some numbers. This is true for any sphere, any mass, any density. But in our problem, we were told that the mass was 60 kilograms. We were told that the density is 19.5 grams per centimeter cubed. Now, before we go on and look at more specific math, I would just like to point out that kilograms and grams are related to each other. This kilogram means it's 60,000 grams. So I've got a gram in the numerator, and I've got a gram in the denominator. My result doesn't have any grams anymore. The grams algebraically cancel out. What I have left over is some centimeters cubed in the denominator of the denominator, which is the same thing as the numerator. So I've got a centimeter cubed that's still sitting in here. I'm going to take the cube root of a centimeter cubed to get a centimeter. Radius has units of centimeter from the things that are given to us. Now we do still have to do these conversions. So first of all, we've got the 3, but this is 60,000 grams. And as long as we do that conversion, we don't have to do anything with this one. And if we want to now, We can pull out our calculator. We don't need this anymore. But what I'm doing is multiplying 3 times 60,000 divide by 4 divide by pi divide by 19.5 is equal to this, which is 734. But I do still have to take a cube root here. So we've got 9.022827. How many of these digits are we supposed to keep? Will I look over? I know my mass is at least one significant digit. Maybe we have two significant digits. Let's just say, for the lack of argument, we've got two significant digits. That 0 on the 60 is actually significant. And because of that, our answer has to be to two significant digits. What we have is 9.0. And that's it, 9.0 centimeters. That is the radius of the sphere that we are talking about. Now, why did I do the problem like this? We were told what the density was right away. We were told what the mass was right away. Why didn't you just plug those numbers in right away? Well, what you're going to find through the course of the semester is when you're doing problems like this, man, everybody might have a different sphere. Everybody might have a different mass. This is not tied to a particular problem. It's tied to how these variables relate to one another. And maybe as you're going through the application of various expressions and how different terms relate to each other, you're going to find out that you casually thought that maybe the acceleration of gravity g was important. But then you put everything together and all of the g's canceled out. So yeah, I could have multiplied by 9.8 meters per second squared here and divide by 9.8 meters per second squared there. But why are you doing this thing that doesn't matter to your problem and putting it into your calculator twice by multiplying and dividing, by adding and subtracting? I mean, wouldn't it have been nice to know right at the beginning that this particular parameter wasn't important? And you can do that with this type of analysis, doing things with variables, not doing things with numbers. Also, what happens if you're going through a problem and somebody distracts you as you're putting your number into your calculator and your calculator gives you a wrong number? If all you were using was numbers, I wouldn't know whether you put it into your calculator wrong or whether you had a misunderstanding. However, if you use algebra, I can see what you were trying to put into your calculator. And I can do an assessment of, oh, this was just some weird problem putting in your calculator. You hit multiply twice instead of once. Or you forgot to divide by 2 or something. I can see what's going on. I can see what you were trying to do. So as you're preparing for exams and doing homework problems, trying to get help and assistance from myself or a TA, if I can see what you were trying to do and not just what an answer is, it's going to be a much better way for me to get help to you and you to get help from me or a TA. So I strongly, strongly encourage doing problems like this, because then at least I can figure out what you were trying to do. And when it comes to the exams, I'm giving you credit for doing things like this, even if you get the number wrong. So there's huge advantage to doing things in a number of different ways, not just points, not just exams, not just being able to get better help, but it really shows a better understanding of what's going on physically. Now that's a good place to stop for this particular topic. I also plan to post another quick video about vectors and how we use vectors and are going to apply vectors. It's another part of this first unit. But good luck as you're continuing on.